Good morning, sir. I'm M. Rakshita from ITA. My topic is about the engineering of software defined quantum key distribution networks. Abstract. Quantum computers will change the cryptography panorama, a technology once believed to lay far away into the future is increasingly closer to real world applications. Quantum computers will break the algorithm used in our public key infrastructure and in our key exchange Pro Tools, forcing a complete retooling of the cryptography as we know it. Quantum key distribution is a physical layer technology immune to quantum or classical computational threats. However, it requires a physical substrate and optional fiber has been the transport of the declared quantum signals. Its integration in a real world shared network has not been attempted so far. Here we show the new programmable software network architectures together with the specially designed quantum systems can be used to produce a network that integrates class classical quantum systems can be used to produce a network that integrates classical and quantum communications including management in a single production level infrastructure. The network can also incorporate new quantum safe algorithms and use the existing security protects, thus bridging the gap between today's network security and the quantum safe network of the future. This can be done in a evolution way without zero-day migration. Introduction. Security has always been concerned when speaking about critical information and infrastructures. Can compromises entire network at all levels cause nothing only large economical losses and breaches of personal rights or losses of critical information, but also damage the public image and erode the confidence of users. The advent of quantum technologies, par- partially quantum computing, has both new security threats which affect most of the existing security Pro Tools. These Pro Tools rely on mathematical problems that are com- compositionally complex using traditional computers. However, quantum computing has demonstrated to be capable of breaking some of the most used. The mathematical basis of algorithms like RSA and ECC are weak under quantum attacks, and so are other common Pro Tools that use them, like Diffie Hellman. The advancements of quantum technologies are bringing quantum computers closer in time. Devices once believed to be several decades in the future are now forecasted to happen within the next 5 years. Albeit predictions are always risky, the trend is clear. Since the information can be received new to the declared later, any communication that is required to remain secret for a few years is potentially in damage today if the protected only with these algorithms. These situations forced institutions such as the US National Security Agency to deprecate the current public key algorithms. metabolism as early as 2015. Other organizations, in particular the ones related to standardization like the NIST, ETSI, IEEE, IETF, IESO, IEC, and ITU, followed suit. Since changing a security infrastructure would require years, it of fundamental importance. There are two avenues to create this quantum safe infrastructure. One is the substitution the current algorithm for others that could resist the attacks of quantum computer, and the other is to use quantum cryptography. The format relies on algorithm complexity, while the latter is a physical layer technology immune to any computational threat. The standardization of both have already started, but it will take time. First, to agree the standards themselves and then to implement them at a global scale. In the case of post quantum algorithms, and according to NIST, the time frame would easily be well within the predicted danger zone. It is thus important to speed the adoption of quantum safe technologies, especially in critical infrastructures. Quantum cryptography most prominent and mature result is quantum key distribution. The QKD technology can be described as a way to provide two synchronized sources of random bits, separate in space and within the property that the information about the bits leaked outside of the pair and can be limited as much as desired. This allows to certain a secret symmetric key between the pair while post the computational power assigned to the adversary. QKD can be mathematically proven to be secure independently of the resources of the adversary. It is an information theoretical secure ITS primate. Also, QKD keys are not correlated anyway away them, thus guaranteeing forward and backward security. However, the physical layer restrictions and the point-to-point nature of QKD has led this technology to be implemented in ad hoc and restricted, usually point-to-point scenarios. QKD technology and networks. QKD is a physical technology. It allows the growing of a secret key that is shared only by the legitimate users of quantum channels connecting them. This channels is usually implemented using optical fiber as a transport media for these quantum signals, qubits. Thus, QKD can be seen as a technology to extend the security premium to the optical fiber used to link them. To prefer QKD, a public and authenticated classical channel is needed in addition to the quantum channel, in particular for post-processing operations such as the key distillation and privacy application. During the installation process of a new QKD device, an initial secret is assumed to be shared among both ends. Customarily named Alice for the emitter and Bob for the receiver. For the first authentication, future authentication rounds between Alice and Bob, not just in a direct link but also in a multiple hop QKD link, are done usually the freshly generated key material. Assume a correct implementation in initialization and no Slide channels. QKD can be demonstrated to be absolutely secure. This means that the information on the secret key leaked outside the emitter receiver pair can be made arbitrarily small. Unlike conventional algorithm, QKD is not based on computational assumptions like the complexity of certain mathematical problems, but on the laws of physics. This makes it restricted to any computational advice like quantum computing. Abstractions model for software defined QKD nodes. The main idea behind the proposed scheme is to be model any type of QKD systems as similarly as possible to any other network elements. Example, router switch. So a SDN controller will be capable of understanding, integrating and optimizing their behavior. Creating such model requires an analysis of which capabilities and parameters from the QKD demand are useful from the network management perspective. For instance, QKD systems are highly complex, have multiple operational hardware and software subsystems whose complexity should be hidden from the network controller. Also, other data produced and maintained by the QKD system, such as internal information or the actual key material, must be kept confidential as they are not required for network operation, and their exposure could compromise the security of the QKD network. These models serves different purposes. Firstly, moving towards the standard interfaces will allow to reduce the time to market of a solution whose major hard stopper is being stuck to point and hog implementations. Secondly, the advent of SDN stuck to point SDN technologies for optical networks facilities the spectrum elections for the quantum channel, and final the centralization of the QKD network management will allow to better optimize generation and utilization of QKD derived keys while maintaining central database of active links and consumer applications. Testbed have implemented a first of a kind SDQKD network in Madrid. The uniqueness of this network is based on several reasons. Field trial on the production network, it is the first demonstrated using a commercial production network. Then 4 fibers connect production points of presence POPs of Telefonica spans metro network in Madrid. No difference was made in the procedures of the initialization of the standard telecommunications equipment, and the QKD devices highlighted their stability and robustness. Continuous variable QKD resilient to noise. The equipment developed by the Huawei Quantum Communications Laboratory in Huawei Research, Germany, has been designed considering the SDN principle as software driven programmable systems. Although the network is implemented using this technology, the SDQKD model definition is designed to cope with any existing QKD, incorporate post-quantum algorithms, additional telecommunications use cases. Furthermore, different use cases, among others to be published, were implemented. Testbed connects 3 Telefonica span pops with their fiber pairs that are part of shared with a Telefonica span, Notra and consumption. The fiber go across other elements that are part of the commercial network, including patch panels and other connectors. They cause losses on the optical channel higher than what can be expected from the distance alone. Abstraction model for software defined QKD nodes. The main idea behind the proposed scheme is to model any type of QKD systems as similar as possible to any other network elements, as CD control will be capable of understanding, integrating, and optimizing the behavior, such as internal informations or the operations, and their expose could compromise the security of the QKD network. This model serves the point to point and a market of the solutions whose major hard stepper is being stuck to optical networks facilities that spectrum allocation for the quantum channel. Conclusions and future challenges. As any technology skill in the applied research phase, QKD has to go through several stages to reach the necessary maturity. Also, for the certification and standardization before reaching market ready status. Apart from the well known issues related to hardware interoperability issues, achievements implements either for QKD networks existing with conventional communications or for separated networks. They also should forces and be suitable for seniors with dynamic quantum channel allocation based on implementation of FCD and fixed schemes. The demonstration reported in this proper presents a clear step forward in enabling the integration of QKD systems in current network operation. Infrastructures, we have SDD principles to produce a converged quantum classification network that have been shared physical and logical infrastructure among quantum and classical channels. The developed network supports the existing security mechanisms and avoids large and upfront deployment caused by allows for staged deployment, and the demonstration in production sites excuses the maturity of the technologies for real and services. Thank you.